What is going on, everybody? Welcome to part 6 of the Python data analysis and data science with Pandas tutorial series. In this last installment, we are going to be talking about applying machine learning to a Pandas data frame. So basically, what is the typical workflow when doing machine learning with Pandas data sets? So generally, if I'm going to do machine learning, first I do all my data pre-processing in Pandas anyways. So it's just convenient to know, okay, well, what's the next step? Like once we've got our features, how do we feed it through a model? So that's what we're going to be doing here. We are going to be grabbing a new data set, and we're going to grab the diamonds data set. So go ahead and download that, put it in your datasets directory. So what's our objective going to be? Well, we are going to be predicting the price of diamonds. So basically this table contains a bunch of values here. We've got the carat, cut, color, clarity, depth, table. I don't know what that means, but it's table percent. We've got the price, the X, Y, Z, which is length, width, and depth of that diamond. So the curiosity is, can we take all of those values, except for price, feed those through a regression model, and predict the price of that diamond, so that in the future, when we get diamonds and we don't know how much to pay for our diamonds, we could just run them through a model. So typical regression task here, nothing too fancy, and the question is, are these features all descriptive enough to give us the price of this diamond? Probably. We shall find out. You can use another data set if you'd like. This one has almost 54,000 rows, which is quite a few samples that we could actually work with here, which is pretty important. For traditional ML, you're going to want probably more than 10,000 rows, I would think. And then if you want to do like deep learning, more than like 100,000 rows. We're just going to use regular machine learning models, nothing too fancy. We're not going to do deep learning here. But if you want to learn more about what we're doing, you want to learn more about machine learning or just Scikit-learn or just basic ML models in general, you can check out this initial machine learning tutorial series here. This one, basically what we do is we go through starting with regression, which is what we're going to do here. Talking about how regression works, we do an applied example using Scikit-learn, and then we actually write a regression model ourselves. And really, we do that with all of them. So we do that with regression, k-nearest neighbors, support vector machines, and so on. So the idea is to learn about the model, learn how to apply it with Scikit-learn, and then how do we write that ourselves from scratch. We do use NumPy and stuff like that, but not using some sort of machine learning library. So it's a pretty cool series. Then if you want to learn about deep learning, check this one out. So anyway, if you want to learn more about that kind of stuff and parameters, because there's a lot of parameters here that we're going to be working with, and if you want to know more, like you feel like you're still kind of in the gray area as far as what all this stuff means, you can check that out, that series out. So now, what we want to do is, let's say you just are a complete amateur, you can check out this choosing the right estimator chart. Basically, if you just Google choosing the right estimator, you will find this. This is from Scikit-learn, by the way, and this is just how you can pick a specific estimator for, and that's your classifier. It's like your model. How do you pick the right one for what you're working with now? So for us, we have more than 50 samples. We do not want to predict a category. We do want to predict a quantity. So because we're doing regression, we want to predict price, so it's a regression task as opposed to classification where you're trying to predict, 1 out of 5 classes. In this case, it's not classification because it's like any price, right? We're trying to come up with some sort of calculation for price. Do we have less than 100,000 samples? If no, then, so if we have a lot of samples, that's kind of confusing. If you have more than 100,000 samples, go with SGD regressor. Otherwise, you should go either here or with support vector regression with a linear kernel. So we'll probably do SVR linear kernel. And again, if you don't know what that is, you just click on it, right? And then this will tell you, okay, here's what you need to do. So, okay, I understand. Right, okay, sklearn import SVM, got it. Here's your classifier, got it. Do a fit, got it. Easy, right? So let's get started. So we're going to import pandas as PD. We are going to say df equals pd.read csv, whoops, not a capital D, data sets and diamonds.csv. Then we also want to say index call equals 0 because this data set graces us with a that's avocado, with a lovely index. Not only is it useless, it's also in string form. Fascinating. Okay, so coming back over here, so we're going to say index call equals 0 because that way we don't generate duplicate indexes. In this case, the index column is completely useless. But one thing you always want to take note of is, let's go ahead and just df.head here. Anytime you're doing machine learning, it's really easy to cheat. Even when you're trying not to cheat, you're doing your very, very best. It is easy not to. So looking at this data set, it's easy to cheat. Anyway, looking at this data set, basically we like all of the columns here are meaningful columns, and then you have price, except for price. Price is meaningful as well, but price is what we're trying to predict. So when we go to build this model, we actually want to use all of the columns except for price. But when we get to that point, I'm going to point something out. And if I forget, someone comment below because it's important. Okay, so that's our data set. Now, one thing with machine learning is all of the data that you pass into your model, at the end of the day, basically all machine learning is linear algebra. Okay, so everything has to be numbers. We have to convert everything to numbers, and ideally, they're meaningful numbers, because if they're not meaningful, they're useless. So there are ways, like, so we have cut, color, and clarity. All of these need to be converted to numerical values. In Pandas, as well as probably Scikit-learn, and I know it's in Keras and TensorFlow, there are always like two categorical methods that you can call. So like in Pandas, we can say df, so for example, what if we just said df cut dot unique? Okay, there's not very many here, but you can imagine a scenario where there's a lot. So this presents a problem. We need to convert these to numerical values. Well, one option you have is df cut. Anyway, sorry, I was still trying to see if that had a meaningful order. I don't believe it does. But anyways, df cut, and then we can say dot as type, and we can convert this type to categorical. Actually, I think it's category, and then dot cat dot code. Let me run that real quick. Codes. There we go. Okay, so this will take cuts. It will figure out, okay, how many uniques are there, and then it just assigns, the first one it finds is 0. Sorry, 0. The second one is a 1, 2, 3, and it just keeps doing that until it's done. It's reached the maximum number, and so it just assigns an arbitrary code to our cut. The problem is we're doing regression, likely linear regression, and we would prefer our values here to have meaning behind them. So because this isn't arbitrary, right? Premium is better than fair, and so on. So we want to preserve that order. So we're going to preserve that order. So just know this exists. So later, if you're doing classification, you just need arbitrary classes. So when you're doing classification, you could use this totally to make your classes into codes. But in this case, for features, we want our features to be meaningful. So we're not going to do that. So instead, what I'm going to do is create dictionaries for all these things. And in fact, I'm going to copy and paste these from the text-based tutorial because there's nothing to glean here. So copy, paste. Wow, let me zoom out a little bit there. A little far in there. And then copy and paste this one. So this will just be dictionaries that we're going to map. How did I know this? Am I a diamond aficionado? No. I found these from the description here of the data set. They order them and stuff for us. So, yeah. So now, interestingly, I started this one at 0. That shouldn't matter, but that's funny. I kind of want to fix it. Let's fix it. What? I don't know how I just noticed that now. But anyway, let me fix that real quick. 4, 5, 6, and 7. I don't really want to pass a value of 0 to my regression model if I can avoid it. Let me fix that in the text-based version. Okay, so now that we have these, we just want to map them. And so I'm just going to come down here and I'm going to say df cut equals df cut dot map, and then we just map cut class dict, right? That's it. And then we're going to do the exact same thing for clarity and color. So I'm just going to copy paste, do this, copy paste, paste, and then it's just clarity dict. And then color dict, so, oops, no, just color is all I want. Color, color, and color. Awesome. So we map all those. Let's just check it with the df.head at the very end. Great. We now have our data set is basically, it's ready. It's been converted. We're ready to pass this through an actual model, sort of. We'll talk about why not in a second. First, we need Scikit-learn. So let's go to our favorite command prompt and do a pip install scikit-learn. We will grab Scikit-learn, and while we're doing that, I'm just going to come back over, I think, and just start typing. So, cool. So we're going to import sklearn, and then we're going to go from sklearn import svm. So, dang it. I want to create space, but I can't because we probably haven't installed yet. Oh, we have. Cool. So, can I do that? Awesome. Okay. So, what we want to do first is anytime you've got data, you want to probably shuffle that data, because the latest thing, often we're going to train in like order, and the latest thing is going to be more biasing than the first thing that model saw. So it's just usually a good idea to shuffle the model, especially if if that data set is sorted in any way. And is this data set sorted in any way? Well, we can come over here, and if we scroll to the tippity top, we can see price does appear to be this data set appears to be ordered by price. Now, so that's a problem. And then also it could become a problem later on. So first I'm going to shuffle this data set just to get it over with. So there's many ways to shuffle a data frame. There's a way in Pandas to do it by shuffling by index, but I don't want to do that because that's ugly. The way Pandas has you do it, I just don't like. And Scikit-learn it's really simple, and we're using Scikit-learn already. So I'm going to say df equals sklearn.utils.shuffle df. Done. That data frame is shuffled. Now we want to assign values for x and y. So in machine learning, generally capital X is your feature set, lowercase y, sometimes you'll see people use uppercase y, are your labels. So x, what is x? X is the feature set. So this is the list of features that points to that label. What's the label? Price. So the list of features is basically everything except for price, right? So this is pretty simple. In this case, we just do df.drop, and we're just going to drop that price column on axes 1, because we're not trying to drop rows, we're trying to drop columns, and then convert that to values. And then the next thing is df, this is just df price dot values. Now, I did say that I wanted to point something out. So let's just run that real quick. And then let's just look at x really quickly. So look at how x compares to up here, for example. It appears that this is indeed carrot. Carrot. I'm thinking chaos. Anyway, this is caret, right? Now, one thing to watch out for. Now imagine at the very beginning that we did not do index call. So if we hadn't done that, this index value here, this, of course, it probably would have been a string. Pandas might have fixed that for us, but imagine it didn't. And now one of your columns was actually going to be index, which is just a incrementing number 1, 2, whatever. Would that be a problem, or would that just be noise? Well, that would be a problem. That would inform the model of price. Why? Because this data set is sorted by index, apparently, because index just increments by 1, and it was sorted by price. So that is one way that you could just, unbeknownst to you, have cheated. And that's the kind of stuff you got to watch out for. It's always just, it's super difficult. You're going to find this kind of stuff happens all the time. It's totally possible that I'm cheating in some way already on this data set, because I haven't spent too long trying to make sure I don't. But so if I do, let me know below. But anyway, that's the kind of stuff you got to watch out for, because it will get you. So anyways, it appears that we've done it right. One way you could always be certain is to, instead of, blacklisting just the price column, you could whitelist just the columns that you want to include. But I don't feel like typing all those out. So that should be fine. Now, X, Y values. Okay, now we want to, I also kind of want to fix, I kind of want to scale. So I think that's what we're going to do now. So SVM, we're also going to import pre-processing. In general, scaling often helps, sometimes only a little. I've never seen it hurt. So generally what you want to do is scale your data, and the target is usually between 0 and 1, but the point of scaling is to simplify your data for a model, because at the end of the day, these models, again, are just linear algebra. So the simpler we can make this problem, the more we can reduce this problem's complexity, the better. So with scaling, we're just trying to bring the range of all these values to something a little more digestible by our model. So I'm just going to say now x equals pre-processing.scale x. On your own time, you can comment this out and see how much of an impact it makes. Or go to the text-based version of this tutorial. I show the difference. I just don't want to, these models are going to take a little bit to train, and I don't want to waste time. So anyway, so we've scaled our data. Now what we want to do is we want to split apart training and testing data. So I'm going to say test size equals 200, because we got like 54,000 rows, so we got tons to work with. Now we're going to say x train, y train, x test, y test. So we want to split apart some number of our data that the model will never see. So x train and y train, these are the things that our model is going to fit against. So we're going to train it on that data. And then later, when we're done training, we're going to test our model on this data, because it's never seen this data. So if you tested it on data that you fit, you're likely to perform much better than on data that it's never seen. So the real true test is always out of sample, data it's never seen. Again, this is a really easy thing to screw up and cheat on and somehow get 100% accuracy, but not really. So keep that in mind. So now, x train is going to be equal to x up to negative test size. So this is up to the last 200 in our case. Copy, paste, make sure that is y, otherwise you'll not be happy. And then this will be x for the last test size. So for the last 200, colon, don't forget that either. That would be annoying. Okay. So now we're ready. Now we define our classifier. So CLF is generally the standard for classifier, equals, and we've imported SVM already, and we'll do SVR, and then we'll say kernel equals linear. And again, if you want to see linear versus, I also run an Rbf. I guess I've already, we clicked, so probably back. Yeah. I also run the, I show SGD regressor, I think Rbf and linear kernel. I can't remember. I might only do Rbf, to be honest. I can't remember. Anyway, if you want to see some, you can check that out, or just run it yourself. See how you do. But anyway, we're just going to do a linear kernel. Then, now we do the training, which is called fit. So CLF dot, not sit, fit. And that's x train, y train. So that process is going to take a moment. So I'm going to go ahead and run that. And I'm just going to glance over it, make sure I did everything right before we waste a whole bunch of time. Pre-process, price, values, blah, 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 blah. Values here, scale, x train, y train, up to the last 200. And then this is the last 200. Okay, great. So now, once we've fit a model, we'd like to know how good did it do. So you can do that with clf.score, and we will score based on x test, y test. The score is going to be an R squared, or coefficient of determination, in the sense of basically 0 is bad, 1.0 is great. Same thing, so like with that, so that's how you would score a regression model. In the case of classification, it will be quite literally, is it right, is it wrong? 0 to 100%. Done. So it's a little more simple there. In this case, this is just like, it's more of a factor of like, how wrong are you? Like with regression, and probably in theory, that's even more accurate, to be honest. So clf.score, okay, and then the score is fine, but especially like with regression, like with classification, the score is like totally obvious. Like, okay, so we screwed up 30% of the time. With regression, you're almost never going to be, you're not going to be perfectly accurate. If you are, the challenge was too easy or you cheated. So the question of like R squared is kind of like super vague, like especially in the sense of diamonds. Like, does that mean we're thousands of dollars off, or are we like just like a few dollars off of each diamond? So if we're only like a few dollars off, like that's an awesome model. So what does that mean? Well, we can just look at it. So instead what I'll do, okay, so we got our answer, and it says we did 0.874, which is actually super accurate. That's pretty darn impressive, to be honest. Cool. So that's a good looking score, or R squared, but now we want to see it with our own eyes. What did it actually predict? So what we'll say is for x comma y in list zip. You don't have to make this list. I'm converting it to a list so we can slice it, because I don't really want to show all of them, I don't think, because it's 200 things. I guess we could show them all, to be honest. Let's just show them all. This is the only one we're probably going to do anyway. So zip, and then we want to zip together x test, y test for x, y. Then we're going to say print, and we'll make this an f string model, and the model predicts clf.predict. And in predict, you always pass a list, and it always returns a list, even if you just want the one thing. So predict x, and then we'll say the 0th, because we're only expecting one thing. So that's what the model predicts. And then we'll just say actual, and actual is whatever y was. Cool. So that should be 200 things, so we'll just print that out, and we can see how quickly that went. And then let's zoom in a little bit. Woo! Okay. So we can see that the model is, close on the first two. Here, the model suggests that we pay somebody to take the diamond off our hands. Probably not ideal situation there. Okay, and then we continue on, and most of we're like in the general ballpark, but some of these are like still pretty far off. But you can see that, like, this $12,000 diamond, the model knew, okay, this is more expensive and more valuable than this diamond, and so on. But we still are off quite a bit on some of these, like this, like negative. So the question is, why is that happening? I don't know. But generally the way that we would overcome something like this, just for the record, is you've got this model, and then generally what you're going to see is someone trains another model. So maybe I will show the Rbf kernel. So get the heck over here. Okay, so what I want to do is I'll just take this, copy, come down here, pasta, kernel, let's do Rbf, fit, great, we'll start that ball rolling, and we will come up here, and we'll just run the score, and we'll do this. And then I'll print this just so we'll see it at the tippity top when it's done. I believe this will take a long time to run though. So I may pause it and then come back, but otherwise I think I'll probably we're basically done here. But I do want to see what that happens. So generally what's going to happen is when you actually use machine learning models in practice, chances are it's not like a scenario where you've got like one model to rule them all. That's not how it works. You generally will do something more like a voting classifier or an ensemble of classifiers. So you'll have 5, 9, 33, 91 classifiers, right? You'll have a ton of classifiers, and then they all will vote. So, or in this case, they will all make predictions, and you'll take the average prediction or something like that. Also, if one of them, like in the case of diamonds, no diamond should be in the negatives. So if one of the classifiers predicted a negative, you would just like toss that thing out, toss that prediction out. So in general, when you combine a bunch of classifiers, they tend that almost always improves. It's kind of like pre-processing. I've never seen it actually hurt unless you use like a horrible classifier for some reason. Sometimes it only helps just a tiny bit, but yeah, if you always want to eke out the best performance, that's a great way to do it. Like you could probably make a voting classifier, and Scikit-learn has methods for doing that. You could probably make a voting classifier and certainly get R squared to be way better. Okay, anyway, quick shout out to the channel's most recent members, Zunki, VJ, Trevor, and Haoyan. Thank you guys very much for your support. You guys help me do what I really love to do, so you guys for that are awesome. All right, we are done. So 55, it definitely did worse in terms of R squared, but if we zoom on in, enhance, we appear to not have any negatives, which is a perfect example of why we tend to use voting classifiers, because while this classifier is less accurate in terms of R squared, it's not doing it as negatives nonsense. So that carries some value. But yeah, you can see it's like way off on a lot of these. Okay. Anyways, you guys can play more with that if you want. See if you can make a classifier that's even better. Or a regression model that's even better. Anyway, that's it for now. If you guys have questions, comments, concerns, whatever, feel free to leave them below. Otherwise, that's probably it for this series. I might add some more later on, but probably not. I don't see what else I need to add about pandas, to be honest. Just check out the pandas docs to learn more at this stage. So, I will see you guys in another video series.